Welcome back, everyone. Is this Friday or is this Monday? Kind of like keeps going in circles, right? It's Monday. How are you feeling about derivatives so far and compared to limits? Better? Okay. Today we actually, again, are not covering anything incredibly new, a little new application of something, but what we're going to do is we're going to use the tangent line now to make approximations. And then we're going to talk about something we call the differential. How many of you will be taking differential equations in your future? Probably most of you. That was sort of like the last major math class I had to take. I got through it. I only got a C, but I got through it. And then you never use it again. So I never got good at it. But what we're going to do today will sort of touch on that idea of differential equations. Okay, so, and it's one of those things, once you get through it, you look back, it probably wasn't as bad as I was making it, as with a lot of things. So we'll go ahead and go through. So linear approximations. What are we doing on Wednesday? Taking a little break, doing some review, going back to 2.4 to 2.8. That'll take chapter 2, start getting us ready for that first test. Get us a little bit of breathing room, nothing too serious. And then we'll get into more applications of derivatives in chapter 3. And then again, we'll take a little break, review that part, and then put the two together. So we'll actually have a 2-day review before the next exam. Okay. So a linear approximation is when we take the tangent line at a particular point, and a nice point, we say by a nice point, we say like integer value 3 or 4, when we're trying to maybe make an approximation somewhere between there, which might make the math a little bit more difficult to work with. But we choose that sort of nice point close to where we want to actually get the approximation. And why do we do this? Let's see if I remember. So here's a tangent line drawn using decimals, so you can kind of see I played around a bit, but the blue line, the slope, the number in front of the x, is really the derivative of the first one, right? The 2 comes down, so that becomes the 0.2 becomes 0.4. And I guess we can, let's see, where is my, well, we'll get to the next. Anyway, so that is a slope, and then I figured out what the y-intercept is. We'll do that. But what I want you to see with this is what happens as we zoom in. So you can see that the tangent line's straight, the function is curved. That's kind of obvious, right? But as we zoom in on this, what starts to become less obvious? The curve doesn't look so curvy. Okay, and it's not that it's really changing, it's just that we're getting very close. The closer we get in, the more that curve, at least locally, looks like a straight line. I think that's pretty, So as long as we're close to that tangent point, we can get a fairly accurate estimate. Okay, so a lot of times we'll do that, and we're also going to see that we can use this because sometimes we've got the function that tells us how things happen in the physical world, but we're relying on a measurement, maybe a stopwatch, to figure out how much time. And there's a potential for some error in there as how we're measuring things, or we're measuring the length of a box and trying to figure, and we make, when humans measure, we make mistakes, or we make errors. I mean, that's part of it. There's a plus or minus. So we're going to see we can use this to figure out what the potential error is and whether it's acceptable, because most manufacturing processes, they know there's going to be some kind of error along the line. They try to reduce it, but they get it within a parameter of errors are okay as long as they're within plus or minus this. So that's the math we're going to use today, is looking here. We know we're going to have a little bit of error if we go with the straight line, but we're going to be close enough for whatever we need to, okay? And again, we do all those parameters in advance so we know how far the error is and whether it's acceptable or not. You know, if we go off and it's not, it's even closer, almost look like straight lines, right? So that's what we're going to do. So first of all, we just have to find the tangent line that will use it as an approximation. We've been doing that already. We can do it graphically, you know, and it will show the tangent line and the equation. If you've got a TI-84, it has it built in. You can use Desmos. We'll look at a few that are not too difficult to go through, but then what we're going to do is we're going to take that tangent line, plug in a value that's close to the point that we actually found the tangent line at, and use that as an approximation. Okay, so here's an example. And this is sort of a technique that was used before graphing, you know, calculators all came in a couple hundred years ago. If you had to find the square root of 9.35, well, you could actually use calculus to find the square root of 9, which is a lot nicer, right? Because square root of 9 is 3. We know that, so that we don't need a calculator for that. And then we can use it to find another value, okay? Let's see if I can remember what I was doing this morning. It's been a long day already. So, what do? Well, we've got this function here. Oh, let's see. Where is my, come on. I need to be able to write. Okay, here we go. Oh, I was using my other computer and then it signs me out. I'll have to remember that. Okay, so now it's kind of a cool little app. It's called Annotate, which works with the Google Chrome, so you can basically get a pin in any application, and it kind of sticks to what you're doing. Okay, so where are we? Here we are. Okay, so what we need to do is get the tangent line to the square root of x function, and then we're going to find that tangent line at x equals 9. Then we will use it to approximate 9.35. Okay, so we'll go ahead and start off with finding our derivative. We'll rewrite it as x to the 1/2. So if we want the derivative, we bring the 1/2 down and we subtract 2 over 2. Subtract 1 from it, right? So that's going to give us 1/2 x to the minus 1/2, which if we want, we can rewrite that as 1 over 2 square root of x. So that's its derivative, right? If we plug in x equals 9 to this derivative, what does that give us? That hurts the S word, right? The slope of the tangent line at 9. That's what it's going to give us. So this is, so when we take the derivative at 9, that's going to give us the slope of the tangent line at 9. So let's do that. 1 over 2 square root of 9, which is 1 over square root of 9 is 3, which gives us that the slope is 1/6. And you could draw the function and everything. So now we've got a linear equation, or we're getting close to getting a linear equation. We've got that this tangent line is y equals 1/6 x plus b. Now if we get b, we'll have the linear equation. And, okay, we are recording. We'll have that linear equation, So what we need is a pair of points x and y. Well, what could we use? Plug it into the original equation, not the derivative equation, right? So we go f of 9 equals square root of 9. So f of 9 equals 3. So that is actually a point, x is 9, y is 3. Okay, so we use that to finish off the tangent line. Or again, you go to your calculator and you put that in and you have it give it all to you, that'd be fine. But y is 3, 1/6, when 9, x is 9 plus b. 9 divided by 6, that'll be 3/2, which is 1.5. So you subtract that from both sides, right? 1.5 from both sides. So what we end up with is that positive 1.5 equals b. Okay, so I took 3 minus 1.5. So now I've got my tangent line. And watch how we do this. So our tangent line is going to be y equals 1/6 x plus b, and b is 1.5. Okay, so now watch how this calculation, we're going to plug in what? 9.35. This is what we want to estimate what is the y value. Will we get exactly the square root of 9.35? No, because square root function's curved. The line we've got a linear function that's straight, so there's going to be a little bit of error, but watch how close we actually end up getting here. So I'm going to plug in y equals 1/6, oops, 1/6, not 1/9, 1/6 times 9.35, and then we're going to add 1.5. So again, we'll see that one. So let's just do the arithmetic on this. 9.35 divided by 6 plus 1.5, just calculate it all together. That gets us 3.05833. Okay, repeating. Okay. Now, again, when we didn't have a graphing calculator, we didn't have calculating tools, that might be a good approximation. Since we do have the tools, let's figure out how close we are. We can actually do the square root of 9.35. And when I did that, I get 3.057. So calculating 9.35, we get 3.05777. Okay, so if we went to the hundredths place, though, we're right on. 3.06, we'd round both of those up to 3.06, and we're good. Okay, so that's how the ancients, 150 years ago, 200 years ago, I don't know, when Newton was around, he's like, what, 400 years ago, 500, something, a long time ago. And this is how they could get square roots. A lot easier than, there's other methods too, but this is using some calculus to get some estimates. Okay. For us, it's kind of like, okay, that's fine, but I got a calculator that can get me those values, so maybe we don't need to use them. But it's this idea of local linearity, and so sometimes you're going to find when you're doing your research or something, you may know the physical function, but using the tangent line may get you accurate enough, and it might be lower on the resource side, and so it's a technique that you'll want to remember. And also sometimes, again, we're going to see the next application is when we use it to kind of figure out how much error there is in what we're doing and whether it's acceptable or not, because we're taking the same concept, we're going to follow the straight line, but we know where the curve is going, so we can calculate the acceptable error that we might have. Okay, but see, nothing really new. Find the tangent line. We've been doing that. That's why we're having you do it. But now we're going to use it. If you follow that tangent line, you can get a relatively accurate estimate. Now, if we want to do the same thing to find the square root of 12, going from 9 to 12 is not going to be nearly as accurate. Right? We're going to have a greater error and probably too much of an error. But, so we've got 9 is an easy one to take, 16 is an easy one to take, but none in between is really easy, so the estimates are not that helpful in those other ones. So that was kind of one thing, using the tangent line to predict a value. And there's only 8 problems in the homework. They quickly move. I think there's 2 or 3 that have you do the tangent line thing. Then they move to something called a differential. And it's similar, but what we're going to look at is, we call a function y equals f of x, and that's what we've been doing all along. So this is really just notation. F of x gives us a y value. So whatever f of x is, if we take the derivative of f, now what's sort of happening on in between, what we've really been doing all along is we've been calling this the derivative of y with respect to x is equal to f prime, a sort of different notation. Notice if we multiply both sides by dx, we get this differential equation. And again, the text will spend a little bit of time talking about how dx and dy could actually be separated, that they are actually values. They're not just a single sort of representative of the derivative, but they're actually 2 pieces. And so you can take dy and dx and move it to the other side, and we can deal with this differential equation. Okay, and it sort of helps us estimate how much the change of y and the change of x, if we know those 2 with the derivative, it kind of gets us close to that. But from the drawing from the text, what you see is the change in x is always equal to the dx part, because of the way we're setting it up. But when we follow the tangent line, what isn't going to necessarily be the same is the change in y to the function might be shorter than the differential. Okay, and so what we've got here is the difference between dy and the change in y. Well, that's the acceptable error that we're going to have. Okay, and a lot of times what that error is caused by is a measurement error. So this is where we use those kind of things to come in. But what we're going to want to focus on is what we use in practice is we're going to do this. So we're going to have y equals a function. We're going to take its derivative. So we're going to get dy times the derivative of that function. We're going to put the dx on the backside, kind of like what we've been doing with implicit differentials. And then they're going to give us some other information about what the change of x is, what x is. We plug those in, and we'll be able to calculate the amount of the error. So we say, if a 3/10 of a measurement is okay, as far as an error plus or minus, what is the resultant measure? Okay, so we'll go through that. But this is, out of this whole lesson, this is basically what you need to remember. And again, just think it was y equals f of x. Take the derivative, dy equals f prime times dx. And you'll be good. So let's go ahead and do an example. We're given y equals this function, f of x, and we want to use the differential. We want to find dy when x equals 2 and dx equals 0.1. So the first step, take the derivative. Again, nothing new, just kind of so we're going to take the derivative of y. The notation we will use instead of y prime, we'll just call it dy, because just different notation. We could do y prime, but it's better. We take the derivative of each of these parts, right? So this is going to be, the 2 comes down, 2 times 3 is 6. Subtract 1 from the exponent, 6x to the 1 power. Over here we have a 1, we bring that down, so we're going to get a plus 6. Minus 1 gives us x to the 0 power, which is 1. So that just leaves 6, and then derivative of -4, 0, so we don't write anything down. So we've got that. But what do we write at the back end? dx, because we took the derivative with respect to x. We could have put a dx on each of the derivatives as we were taking it, but then we would have factored it out. And so I just kind of say, let's just take it all and then say, let's group this and say at the end dx. Okay? We okay with that? But again, if you want to practice, you can bring it over. So this is what we're going to use. They say find dy. The cool part is we've got dy is isolated, right? What do we need to do? Just plug in 2 for x, and then the dx we plug in 0.1. So it's kind of saying we're allowing an error of 0.1 in our measurement of x, our change in x. And so we can dy equals 6 times 2 plus 6, and then dx is 0.1. And we just, it's arithmetic now. See, that's 12. 12 plus 6 is 18 times 0.1. So that's going to move the decimal place over one place. So dy would be 1.8. I think that's what you'll see is that there's a difference, though the change in y is actually 1.8. So if we plug in 2 versus plug in 2.01, we're going to see the change in y is going to be off by about 1.8. So again, if we use this estimate, it's kind of giving us, if we make a error in x of 0.1, we're going to make an error in y of about 1.8, plus or minus. Okay, make sense? Techniques are pretty straightforward. Just use that dy equals derivative of f times dx. Took this one, changed it a little bit. I'm doing 4 seconds in the book, or the WebWorks might have it a little different, but let's apply the same thing. And this one's a little more understandable because it actually has the context involves a measuring error. So the distance in feet a stone drops in t seconds is given by dt equals 16t squared. So, and 16 is the force of gravity, and I think it's in feet per second. If you do it in meters per second, there's a slightly different constant, but that 16 means it's dropping. So what we could do is we drop a stone into a well or to a hole. We listen, and we start the timer. When it hits the bottom, we stop the timer, and then the amount of time we could figure out how deep that hole is. And if we did it accurately, we could get very accurate. But they're telling us that, so we do all that, that there's a measurement error of 3/10. If you're like, because you're either going to anticipate, maybe stop a little early, or you're going to miss it and stop a little late. But that's, you know, human reflexes. I mean, the better reflexes you have, the probably the less error, but they're willing to accept a 3/10 of a second error. And maybe it's the machine, whatever it is. So we want to use linear approximation, which is what we've been doing, really the differential, to estimate the bound for the propagated error if the measure time is 4 seconds. So they're saying that x is going to be, or t in this case, is going to be 4 seconds. Okay, so what we're going to do is we're going to write this equation. Instead of dt equals 16t squared, we're going to go with y. We could go ahead and leave t, or you could change it to x. I have a problem. If I change it to x, I might put my answer in as x, and then the thing marks me wrong because I did, you know. So I'll leave it as t. So what do we want to do? We want to get the differential equation. The differential, take the derivative of basically of both sides. So the derivative of y is 1 dy. The derivative of the other side is going to be the 2 comes down, multiplies times 16, 16 times 2, 32. Subtract the 1 from the exponent, so that's t to the 1 power. And then we've got the dt. So far, makes sense? So this is, and we were actually doing differential equations. Wow, it's a 300 level class, and it's a scary class that everyone says you can't, it's not that bad. If you really think what you're doing, it's an algebra mixed with, and it says the guy who only got a C in it, right? First time through it was because I bought into everybody's fear mongering. If I would have just went in straight in, I probably would have done a lot better. So what we've got is, we've got the amount of error we're willing to receive, 3/10. That's dt, that's a change in t. It was supposed to be like right on, but there's a possible error of plus or minus 3/10. That's what dt is. So we put that in there. So this is, dt is just gonna be 0.3. Usually like. And what is t? T is the actual measured 4 seconds. Okay, so that's going to go in here. And what we're going to get is as they called it, the propagated error, the potential of error. And this is a plus or minus. So this is the limit of the error. Now the actual error might be less, right? Because maybe we've got somebody with faster reflexes and they were really only off by maybe 0.01. But what this gives us is the amount of error we're willing to accept. And say that on general we're going to get it. So if we multiply all that out, what do we get? 38.4. Okay. And what does that mean? If we plug it into the original equation, 16t squared, that'll give us what our measurement is. So we put 4 into there. So let's do that. So what is, because we're actually, for the second part that I'm going to have you do, we're going to need that. So d of 4 is 16 times 4 squared. 4 squared is 16. 16 times 16, 60, no, not 64. 126? 256, yeah. I know it was one of those numbers, bigger, 256. So what this is, so now let's try to get the context. We found because it took 4 seconds, that the well should be 256 feet deep. But what now does that 38.4 represent? The error. The error that it might be 38.4 feet deeper than that because our timing, maybe it was actually 4.3 seconds, or maybe it was actually 3.7 seconds, so it's 38 feet less than that. So that's actually 30, that's almost 40, so that's almost an 80-foot difference, right, plus or minus. That seems like a big error, but we're willing to accept it because or at least that's as accurate as we can get with the timer. So the other part of this is that a big error or not? A lot of times what we want to do is turn it into a percentage, a percent error to kind of figure it out. Because right now for me, 80 feet, the difference of an 80-foot, either short or long, if I have to dig it, if I'm short by that much, maybe I got to go 80 feet more. So I don't know. So how do we find the percentage error? Well, we take what it was supposed to be and we divide that into the error. So, and again, some of the problems will have you do this. So we're going to take 38.4, which is the propagated error, or the amount of the measured error that not the measured error, the error in the depth of the well because of our measurement error of time. And then this is what it was supposed to be. If it was actually, if we hit it right at 4 seconds, it should have been this. And this will give us a decimal. Let's see, 38.4 divided by 256. It's about a 15% error. So, a 0.3 seconds in timing error ends up being a 15% error in the way that we're measuring. So 0.15 or 15%. And again, it's always good to put the plus or minus because it could go either way. and I guess we're really just 40, we're either 40 feet short or we're 40 feet long, but to me that's a difference of 8. So 15% error. And then we could say, is that, okay, if that's not acceptable, then we go to the next level. We're gonna, let's go get a laser measurer, because those are more accurate. We need more accuracy, okay? Or, is this okay? Yeah, it's okay. Then we could use this method, okay? So that's what you're gonna, I mean, it does have copious engineering applications. Because again, in manufacturing things and engineering things, we know there's going to be an error, but we just have to know how much that error is, how much is acceptable, and then that's what the calculus allows us to do. Okay, and it's really not that bad. It's not that scary when you call this is a differential equation. I think that was my biggest thing. I went to that class so scared because everyone told me, oh, everybody fails that class and stuff. It's not that bad. So that's all we got to do today. Linear approximations using the tangent line, using the differential equation, which really was, taking the derivative of both sides, multiplying by the error in there. And we did one of the problems. It'll be very similar to that. There is one that will ask you for the amount of error. That's what we did the first time. When it asks you for percent error, you have to calculate what the measurement's supposed to be, divide them out, and you'll get that as well. Okay? And then Wednesday we're going to go back and review. So take a look at the exam review, see if you have any questions, or the homework. Feel free to bring any questions in. Feel free to send me questions by email, so then I'll do those first. Wow, you got done early. It's really early. I gotta do something else. Yeah.